Welcome back to ECE 320A. Trying to remember where I'm at. I should know by the location what class I'm in, but still getting used to that. There is another homework assignment. It hasn't yet been posted, but it will be due, I think, a week from Saturday. I think that's the 7th. That's the idea. And it will be dealing with convolution, Bode plots, and the material today, which is filters, is the idea. And you have background material available to you. What I'm going to try to do is give you maybe a little different take on that same information today and the next time we meet, which is, I guess, in a week. We will meet again and we'll be talking about filters, I believe, at that point as well. What I want to do today is remind ourselves of where we are with respect to filters, what kind of filters exist, and how we can actually realize those. We've already talked about that before as a passive circuit. And then we'll get into active filters or active devices, op-amp-based filters. What are their advantages, disadvantages? And then we'll derive a transfer function. So the derivation will connect what today is talking about with respect to filters. It'll connect transfer functions. Maybe we'll sketch the Bode plot. It'll start to bring all of this together, hopefully, and you'll start to see how it fits. Last time we talked about Goldilocks, and so I assumed you were wanting to continue with storytelling. The first part of today, I am going to just be telling. Just kind of telling you what's on the slide, which don't fall asleep, but try to keep track of some of the distinctions. This is now chapter 14 and chapter 15 in the textbook. Chapter 14 is passive filters. Chapter 15 is active filters. And today we want to think about one and the other or both and how they are related or how you can think about them in terms of what they provide for us. And to get comfortable with filters, obviously you need to be comfortable with frequency response, which is why we talked about Bode plots last time. You know the drill or the types of filters. We have low-pass filters, and now you should be able to quickly sketch a passive realization of a low-pass filter. That's just an RC circuit. And you should be able to analyze that in the time domain, but in this class it's mostly in the frequency domain. Can you find the transfer function? Which the answer is yes. And can you now find the response due to any input, where here the input is V sub I, and now can you, if you have found capital V sub 0 of S, can you find what it looks like in the time domain by doing inverse Laplace transforms? All of these concepts should be coming together. In this particular case, we have the roll-off rate as minus 20 dB per decade, or we could call that minus 6 dB per octave. And we're using those two slopes interchangeably. And what's an octave represent? A factor of 2. So it's now doubling our frequency, and that now allows us to talk about maybe smaller expanses of frequency and how far down we need to be relative to a given location. Low-pass filters, then, you might use if you're doing analog to digital conversion. You might want to now reject some high frequencies or provide a circuit that does some anti-aliasing filtering for you, or you could think of this as some way to remove noise, that the noise is at a higher frequency versus the signal that you're interested in. High pass filter, we use a dual element. We use the inductor now to replace the capacitor, and we can now derive the transfer function for this passive circuit, and that's now SL over R plus SL in terms of impedances. And here, again, it's first order, which means we have the first order slope, and the corner frequency or the break frequency is related to the R and L parameter values. It's R over L, and this can be used to get rid of DC or low frequency signals, in contrast to what we were doing with the low pass filter. We can then start putting some of these pieces together. And now we can say, oh, we can combine those first two in a convenient way to produce a bandpass filter, where now we're focusing on a central region of frequencies. And we know the circuit that we can use to make that happen. Again, maybe you don't know which configuration or orientation to label as your output and which one's your input, but you could derive the transfer functions fairly quickly, and then I hope do some rough Bode plot sketches to convince yourself, oh, this one now has a bandpass behavior in terms of its magnitude frequency response. Again, I'm going through this kind of quickly, but I'm hoping you can, if you don't take everything down, I'll make the notes available and you can fill in where needed from the notes on the course website. And finally, the last filter type that we've talked about, again, uses a second order system, an inductor and a capacitor in series with a resistor, and now we're measuring our voltage across the two energy storage devices, the L and the C, and this now gives us a band reject filter in case we want to get rid of some hum that might be occurring at a frequency that we know is there, maybe 60 hertz, or maybe there's another frequency that we're trying to reject. We can now select these parameters for a passive device to accomplish the rejection of those frequencies. And the name lets you in on the shape or the structure of the magnitude response that you would be expecting if you sketched it for this transfer function between the input V sub I and the output V sub 0. Those are what we've talked about already. Those are passive filters. You can also create filters to do similar things using op amps. And here are some advantages of pursuing active filters. One, we don't have to use inductors, and those can be heavy and expensive. If our application doesn't need it, then maybe we can get away with an active filter. We can now scale or amplify the signals going through, since we have the ability to amplify with an active device versus the passive devices. Those are not having really any built-in way to give you amplification. And the other nice thing about, or an advantage with active filters, is we can start applying resistive loads or some other kind of load to the output of that circuit, and it's not going to load it in the same way as a passive circuit will. A passive circuit, now you load it and you've now messed up maybe the break frequencies that you were expecting, because now you have a slightly different circuit configuration. The active filters, allow you to think maybe more in terms of black box building of these subsystems to produce the result that you want. Those were the advantages. What are some disadvantages? Well, an active filter you actually have to power. So now we have to create these power supply rails, or these power supply rail voltages, to even energize our op-amp to make it function. Likewise, these op-amps and the resistors around them can inject noise into our system, and we may not want that there, whereas the passive devices won't have that kind of noise characteristic present. And because of that, now we may not be able to use an active filter when we have a very low level signal that we are trying to filter. If we're now picking up some radio signal from an antenna that's very low level, it may be difficult to distinguish between what's the signal and what's the noise produced by our op-amp circuit itself. And we really want to be able to distinguish between signal and noise. We also are unable to be using these active devices, these op-amp based filters, when we are trying to filter high power level signals. For example, after or in a radio transmitter, we won't be able to use these op-amp based filters. We maybe have to resort to some passive device. And something that we typically don't worry about until we have to implement something is the gain bandwidth product of an op-amp. That we can't neglect. And because of that, the bandwidth of the filter that we are trying to create or produce may be restricted. We have to make sure that it's a lot less, maybe a factor of 10 or 20 times less than the gain bandwidth product of our op-amp allows. And that's maybe a disadvantage of going with an active filter. Bottom line, a lot of times your answer can generically be it depends. And that's true here. Are we going to use passive or are we going to use active? It's going to depend on the situation. Here, a lot of the disadvantages that I just tried to make you aware of may not exist for the filter that you're wanting to build or create. And if that's the case, then you'll probably go with an active filter, especially if you're working with frequencies less than 10 megahertz. So there's the fireside Goldilocks fairy tale story that I've now read to you from the screen. Now we can start to exercise our hand and our mind to try to do some analysis on a active filter and see if we can now derive the transfer function. Here is a circuit provided as a problem in the textbook. It's problem 1533C, and now we want to be able to find its transfer function. What's the transfer function between V sub I and V sub O? How do we start approaching that problem? And let's not worry, now that I made a big deal about the power supply rails, let's just assume that those are sufficient to not have saturation in this circuit operation, or in the operation of this circuit. We have 2 resistors, 3 resistors, and 2 capacitors, and the capacitors have the same value, which is why I haven't subscripted those capacitors. Maybe I should have subscripted those capacitors so that you could see, as we're analyzing this, where those particular capacitors are in our equations. But hopefully it will be clear from our analysis. I'm assuming, since I'm teaching 220 this semester, that you've seen this already in 220. Is that true? I'm actually kind of kidding you a little bit. I'm pulling your leg. We didn't go quite this far in 220. Have you already done one of these in this class? Yes, no, no. How do we start? What's one of the first questions you want to think about when you're dealing with an op-amp circuit? Do we have feedback, and is it negative? Do we have negative feedback, and what's the significance of negative feedback? The negative feedback is trying to force the inverting pin and the non-inverting pin to be at about the same potential. It's trying to make V sub P approximately V sub N. If you don't have negative feedback, then your output's going to swing basically between one of the 2 rails depending on the sign of the voltage between your non-inverting and inverting pin. But we do have negative feedback. We have feedback from the output, maybe not as direct as you might always be thinking, but there is feedback through R sub 3 to the inverting pin of the op-amp, and it's even interconnected in other paths as well, but we do have negative feedback. So here we have negative feedback, and that means that we can make the assumption, and in fact, since I said let's not worry about the supply rails, we're just going to assume that this isn't going to be operating in saturation. So we're assuming now that V sub P, which is what I'm calling this, is now approximately V sub N, which is what I'm calling this, are the same. And in this case, since V sub P is connected to common, so is V sub N. That non-inverting pin and the inverting pin, we're going to assume are at common or at our ground location. And I don't know if I even refer to it, but now when we compare, if we're trying to find a potential across certain elements, we'll be able to use the fact that the inverting pin of our op-amp is at a potential of 0. Now what? Now what do we do? Pardon? KCL. So we can do KCL. Actually, we have a couple of nodes that we could write KCL at. Here is, that's sort of making me nervous, but now we can just lump all of those together. That's now the same node, and we also have that node as well. Let's call this one, and maybe I'll change colors so that things will... Let's call that node 1, and we'll just call this voltage V sub 1. And if we now are interested in KCL at that node, we can just say, well, the sum of the currents out of that node sum to 0. and we have 4 currents going out of that node. Let's then just write the equation relative to KCL at node 1. The current going left horizontally. And now we're assuming V1 is a node voltage we're trying to determine. We don't know what it is. V1 and V sub I we're assuming we know. That's an input. We can write the voltage dropped from right to left across that first resistor R sub 1 as V1 minus V sub I, and the current then just is dividing by R sub 1. The current then going to the left is now V sub 1 minus V sub I over R1. Plus, let's work our way counterclockwise around that node. Now we have what's the current going down through that resistor. That one's fairly straightforward. That's Ohm's law gives us now V1 over R sub 2. The current going to the right horizontally. It's where we are, V sub 1, minus where we are going, which is V sub n, but we know that V sub n is actually 0. So it's just V1 divided by the impedance of that branch, horizontal branch, going towards the inverting pin of our op amp. And then finally, the current going up. Again, we're sitting at V1, and where are we going? To what voltage? We're going to V sub n again. That's that wire that's connecting everything together, and that's at 0. Again, we have then a V1 over 1 over SC, and the sum of those 4 sum to 0. That now we can combine all of the terms that scale V sub 1. We can push the V sub I term to the right-hand side of the equality sign, or add V sub I over R sub 1 to both sides, and we now have 1 over R1 plus 1 over R sub 2 plus SC plus SC V sub 1 is equal to V sub I over R sub 1. If we collect all of those terms in square brackets over a common denominator, let's call that now R1 and R2, we now have R2 plus R1 plus 2 R1 R2 CS. Scaling V sub 1 is equal to V sub I over R sub 1. Can cancel the R sub 1, and we can solve now for V sub 1, which was the node voltage, one of the node voltages that was not yet known in that circuit. We now can say that V sub 1 in terms of V sub I is R2 over R1 plus R2 plus 2 R1 R2 CS times V sub I. That's one of the unknown node voltages, the one at node 1 relative to the input V sub I. Let's now write a second node voltage so that we can introduce our output voltage V sub 0 into the equations that we have available to basically find the transfer function between V sub I and V sub 0. And hopefully that will allow us to get rid of V sub 1 and get the transfer function that we want. We can now think about the current flowing in or out. For some reason I'm saying let's do it in on this one. So we now have that current going in. That current, which is what? That one's 0 because of the high input impedance, so we really don't need to worry about that. And let's have this one and that one. We now have effectively 3 non-zero currents going into that node, the big node, the encircled node, to write a KCL equation with respect to. We clear on what we're doing or why we're doing it and how we're doing it? Yes. Is there a reason why I make all the currents going in instead of going out? Nope, just to confuse maybe. I'm just showing you that it doesn't matter. You could have said, you know what, I feel more comfortable going out. So now you could sum all the currents going out. Or you could just say the algebraic sum of however I've labeled these currents need to sum to 0. KCL is true. It's just how you have labeled your diagram and how you want to write it. Let's now write KCL at N, where N is the inverting pin of the op amp. Now I have 3 horizontal currents. Let's see which one I want to talk. Which one do you want? Where do you want to start? Let's start at the bottom one and then go clockwise this time since we went counterclockwise before. The bottom horizontal is now V1 over the impedance presented by that capacitor, which is 1 over SC, since V sub n is 0 volts. Now let's just go vertically up from that horizontal and write the next one. In fact, that's exactly the same expression. We have V sub 1 minus where we're going, which is 0, divided by the impedance, 1 over SC. Oh, now I know. Now I have a better reason for your question. No, red and blue are in the same direction. Makes no difference, but I just saw that and thought I would justify. That's a key observation. No, it doesn't matter, but now we're flowing in the same direction, and I had to use red and blue. You know why, correct? Pardon? Wildcats? Yeah. Go Wildcats, right? Is there a game today? What's today? Tuesday? Okay, let's get back to our business here. There is our next current, and then our final current is actually going to the left, and that's now V sub 0 minus 0 over R sub 3. And those 3 sum to 0. Or taking 1 to the other side, let's solve for v sub 0. Take the other two terms to the other side and multiply both sides by r sub 3. And the other two terms, the SC in the denominator of the denominator gets upstairs, and we have 2 of those. And taking them to the other side gives us the minus. Oh, and let me just make it a little bit more. And we also had V1 being scaled by those parameters. We can now combine this V1 or use this V1 expression into that location or that slot, and now we will have eliminated the one node voltage that we didn't need necessarily, and we have a transfer function between V sub I and V sub O. Our transfer function now can be identified from the relationship of V sub 0, and now for whatever reason I'm showing you that we're in the frequency domain. Upstairs we have minus 2 r sub 3 cs, and downstairs, oh, and we also have an r sub 2 in there. And downstairs we have the R1 plus R2 plus 2R1 R2C times S. And there's our transfer function. Do you see what kind of, yes? I don't know, the typesetter on this machine is a little bit funky. That was an I. You missed it? So that was supposed to be the input voltage V sub I. Thank you. Forgot the dot. Actually, it didn't have much of a curl to it either before, was it? I was in my own little world. I guess I was seeing that V sub 1 up above and I just copied it down. But this is now the transfer function we want. Do you see the frequency response from that transfer function? And if you don't, that's okay. I'll forgive you this time. But let's figure out what that could be. Let's just assume some convenient values for these parameters and then sketch the resulting transfer function's Bode plot. And for convenient value, let's just let everything be 1. Suppose R1 equals R2 equals R sub 3 is equal to 1 ohm. And let's just go ahead and let C be 1 farad. And with that collection of parameter values, the numerator becomes minus 2s, and the denominator 2 plus 2s. Or 2's are wild, we can cancel them. They're everywhere. Let's just go ahead and get rid of them. And now that wasn't supposed to be a plus sign, that was an equal sign, is now minus s over s plus 1. I caught my error before you had to correct me. But usually I can look at the faces of the audience and see that something's not quite right on the board or on the screen. They're looking at me a little differently. All right. Now do you see the Bode plot? Or just in general, could you sort of see? Now you have your virtual helmet on and you're seeing that frequency response. What's happening at low frequencies? Or now you might say, do I have any poles and zeros at the origin? Yes. You have a 0 at the origin, and what's that Bode plot term produce? Yeah, we just have to walk over to the wall and pin it on the wall, right? It's coming from 0 in an absolute sense, so it's coming from way down in a logarithmic setting or in a dB scale and going up at what rate? What's the slope on that 0 at the origin? There's just one, and that now gives us the 20 dB per decade. So looking at this, if we just wanted the frequency response's magnitude, we could neglect the minus sign and say, oh, I'm coming up from the bottom, and then I have a pole at 1, and that's going to essentially cancel the rate of change of my magnitude, and this is the shape that I would expect from that transfer function in terms of its magnitude. Now let's verify that more explicitly. Let's now step through the process of sketching the Bode plot. And in that sense, I would just start identifying the terms. I have a 0 at the origin. And is it in time constant form? Is it in pole 0 form? Is it in any form? Does it have a form? Pole 0. It's also time constant, isn't it, for this particular transfer function. So you could have been right. You could have said all of the above if that was an option. Unless I said, I don't know, some form that it wasn't. But it's the two forms that we are comfortable with. It's time constant form and pole 0 form at the same time. And we could maybe even say, if this is important, which it will be for our phase plot, it won't influence our magnitude plot, but the constant is actually -1. And we can think of that now more in terms of a magnitude of 1 and a phase. What's the angle of -1? Pi. Is that a negative pi or a positive pi? We're getting close to the holidays. We have to figure out what kind of pie we're dealing with. Right? What pie do we have? Fruit pie? Cream pie? It's 3.14, right? That pie. And it doesn't matter, plus or minus, but I usually think in terms of minus because that allows me to think more in terms of delay than advance. So this either way would be okay, but I typically would prefer to just probably use the minus 180 degrees. And we'll need to worry about that. It's not going to impact our magnitude plot because the gain or the magnitude is 1, but the phase it will influence. It will scale everything up or down by 180 degrees. In this case, I'm saying let's shift it down by 180 degrees for all frequencies. We also have now a pole and it's just one pole at -1 radians per second. Now we can do our Bode plots. There's our frequency axis, which in fact is log of omega. And I'm sure most of you went home and hand wrote out what log of 1 is, log of 2, log of 3, log of 4, from your calculator maybe. Pardon? Yes, you could use your slide rule. Okay, this is a challenge maybe. See if those are on sale for Black Friday. If you can find a slide rule on sale, you can send me an email. I might even wake up at 3 to go get it. Because I know there would be a demand. There would be a rush on that. That would be like a doorbuster special, right? On extra credit for me? I don't know. We'll see. I need as much extra credit as I can muster. Where are we? Oh, at the store at 3 a.m. trying to find that slide rule to find our logarithmic table. But here, let's just do this. Here's H in dB, and our frequencies aren't too critical. We have a pole at 1, so we need to be at least splitting that or putting that in the center of a couple of decades. Let's now just say this is 10 to the -2, 10 to the -1, 1, 10, and then 100. Oh, and those are, you might want to get a ruler too at that Black Friday, because my spacing is a little off. Those are supposed to be the same distance apart. And what terms do we want to sketch? Well, let's sketch, let's do the 0 at the origin. And now that point is -20 dB, so this one's now -40, and this is +20. I shouldn't have done that, but should just draw the line and then say there's my scale. This is now my 0 at the origin. And the slope is +20 dB per decade. What about my pole at 1? And I'm assuming this is my 0 dB line. That allowed me to indicate where I was crossing 0 dB at omega equal to 1 with my 0 factor at the origin. I have a pole. It's 0 dB until we get to 1, and then it goes down at the same slope as the 0 was going up. So this is now -20 dB per decade. And my gain constant, if I had one, let's say I had a gain of 10, absolute. Then the log of 10 is 1, and I would have had 20 dB of gain for all frequencies. I would just shift, or I would introduce that as a flat line here, and that would tell me whatever I've created, I now shift all these points up by 20 dB at all frequencies. Here I'm shifting everything up by 0 dB since my gain was actually 1. Now I have all of these pieces. How do I put them together? What's my overall Bode plot? If I now said Bode of G or Bode of H in MATLAB, it should produce the overall. Now I'm just adding these up point for point. I add 0 dB onto this, And now I just climb up this curve, and then at this point I have a plus slope and a minus slope that cancel. And that's now my total magnitude, where this was the pole at s equal minus 1. And everything was sort of happening in this case at omega equal to 1. That's the magnitude. Now let's draw the phase. What pieces or parts do I have now? Which one do I want to worry about? We have a minus 180 for the constant, and I was actually going to do, well, I'll just do it in blue. So now let's say that's minus 90 and here's minus 180. What else do I have? Do I have any other angles to worry about? My transfer function was minus s over s plus 1. Do I have to worry about the s upstairs? And how can I think about that? If you now said, oh, you have a 0 at the origin, I don't know what color to make it. Let's make it blue, I guess. So here's our S-plane. And now as I'm walking up the imaginary axis, for each omega, what's my angle? I now am measuring the angle with respect to the positive real axis, and at omega equal very tiny, I turn 90 degrees. At omega a little bigger, I have to turn through the same angle. It's always 90 degrees. Do you see that? This angle now between here and there is always 90 degrees. That means then that, and it's upstairs, so now I have a plus 90 degrees. For that factor. And if I just had those two, if I just had a transfer function of minus s, and I considered the minus to be minus 180, my total response would just be minus 90 degrees for all frequencies. I just add those two point for point at each frequency. I don't have just a differentiator. That's what h of s equal to s would be. That would be like a differentiator in the time domain. we have a pole factor. And now we have to consider its contribution. And how do we account for the pole? Where is the break frequency on the pole? And how much angle does it start with, and how much angle does it eventually end with? The pole factor. Again, if you're not clear on what I'm asking, you could, where did that come from? It's very appropriate, though. I'm glad it was there. Who's playing with my OneNote? Thank you. But we have a pole at -1, and now we are at J1, the break frequency, omega equal to 1, and what's the angle? I again measure it with respect to the positive real axis, and I now have to look through a 45-degree angle. If I was at low frequencies, let's say that's the dot there, then what's my angle when omega is small? What's the angle of 1? And as I get bigger with omega, which that's not J100 in the scale that I'm using, but now omega large, the angle of J omega plus 1 is now 90 degrees, but since it's a pole, since it's downstairs, it now gets subtracted. Do you now believe me when I say we start at 0 and we end at -90? Now, how do we connect those two extreme values? Here we're doing straight line approximations. We connect them with a straight line. Where do we start seeing phase in our straight line approximation? Seeing phase other than 0 degrees. Now you have to recall Goldilocks, right? And say, oh, what's small and what's large relative to this break frequency, omega equal to 1. Small is a decade below that. We start then changing at 0.1, and we start and we say we're already maxed out at the largest angle, in this case -90 as we can be, a decade beyond that break. Our angle is changing for a single pole factor. It's changing over a 2-decade interval between 0.1 and 10. Yes? So why is it -90 and not +90? But let me first draw this. And now this, what's this slope? It's now -45 degrees per decade, and it's going through -45 there. Now the question was, why is it -90? Here, let's say we now have a pole factor. You can now think of this as, oh, I have some magnitude at some angle, and your angle now is the inverse tangent of omega over 1, but we can also think of that in terms of complex exponentials, because the phasor notation is just a convenient notation. This is really magnitude at e to the j and that angle. Can I call that angle theta? now I just rely on my properties of exponents and say, oh, if something was downstairs and I wanted to combine it with what's upstairs and it's in the exponent, I just subtract my exponents that are downstairs. That's where the negative comes from. Our negative, anytime we're downstairs, we're getting negative slopes and negative angles. And now we have this 1 over e to the minus j theta. And theta from our sketch here, that angle in our sketch is 45, it is 90. We just have to realize that it's being provided to us by a pole, and that pole is downstairs, so we have to associate the negative sign with that angle. Yes?
For that S-plane, shouldn't the J and like the J100, shouldn't that be negative? Because the breakthrough frequency is at negative. Well, not.
So, okay, the question I think is, it's confusing why we have poles that are negative, and then we're talking about positive angles when we start doing the Bode plots. I'm kind of paraphrasing and maybe misrepresenting your question, but in fact, we are just worried about positive frequencies. We're going from 0 up to infinity on the j omega axis. And in the frequency domain, when we're thinking frequency response, now we are simply, so if we had some g of s, in this case it was in fact that we are replacing s with j omega, and now we just worry about what that complex number equals at various frequencies omega, where those frequencies are going from DC 0 up to infinity, omega going to getting large. Not sure, did that answer your question? So the fact that we have it is important that we keep track of, in the g of s expression in the transfer function, it is critical to keep track of what values of s that either goes to 0 for zeros or blows up for poles, or when does the denominator go to 0. And those will be negative, and we want our poles and zeros for our Bode plots that we're plotting to be in the left half plane, which corresponds to, or is used the terminology, that's a minimum phase system. And the reason that is true in terms of minimum phase, we could say something like the following. Suppose that I now had a 0 here at minus, well, let's just be very concrete, at minus 1 versus a 0 at plus 1. And we're comparing these to the characteristics of these two zeros. If I'm now looking at the magnitude relative to the one in the left half plane, I'm looking at that hypotenuse. And if I looked in the right half plane, I would be looking at that hypotenuse. How do we compare, or how do the magnitudes compare between the two different zeros? They're the same, aren't they? So whether we have a 0 or pole in the left half plane versus the right half plane, their magnitude response is going to look the same. It's in the phase response that it's different. Let me make this a little bit bigger so that I can have more space. But now let's say that we were up to this dot. If my diagram was drawn properly, those hypotenuse lengths would be the same. But now what are the angles? Here's the angle due to the positive one. And here's the angle due to the minus 1. Which one's the minimum phase? Which one's the minimum angle? It's due to the zero factor that was in the left half plane versus the one that was in the right half plane. That's why the terminology, oh, it's a minimum phase system, means that all of your poles and zeros are in the left half plane. And that's how we are sketching our Bode plots, or that's how we're getting. So here's our left half plane, and here's our right half plane. And we need everything here to provide us with a minimum phase system. Questions on that? What if looking at the time, trying to see how much time I have left, what if we wanted to have a faster roll-off into our stop band? Let's say we were designing a low-pass filter and we say we need to be attenuated much quicker than what a first-order filter is attenuating. I've kind of given you the answer. You can use a second-order filter or a higher filter. Do you see now that when we're designing filters, that may not cut it if this is now minus 20 dB per decade. If we needed to be attenuated by some amount at that frequency. That means that somebody might say, well, let's just increase our filter order. Let's make it a second order. So here was n equal 2 for our factor, and here's n equal 1. And let's now say this is minus 40 dB per decade. Maybe somebody says, well, that's still not enough. So you say, well, give me another one. This is now minus 60 dB per decade. And you're going, well, I know all there is to know about designing filters. I know how to design a first-order low-pass filter, passive. And if this is V out and this is V in, my transfer function, going through all the steps, and that simplifies then to 1 over S times RC plus 1. Suppose that we said, oh, just worry about a normalized filter. Let's say it's normalized to have a pole at 1. That allows us to just think about R and C both equaling 1. And many times our initial steps in the design process work with normalized filters, which might have a transfer function for this first order as 1 over S plus 1. Now, suppose somebody says, oh, I need more attenuation at higher frequencies. And they say, well, just give me another factor of 1 over S plus 1. Will that give me the same bandwidth as a single factor, 1 over s plus 1. And what am I defining as my bandwidth? I'm defining as my bandwidth the frequency where I am minus 3 dB below the DC level. If we look at the normalized first order, what's the break frequency or what's the cutoff frequency or what's the minus 3 dB bandwidth? And in this case, we could say, where's your pole? It's first order. That's where it's at in terms of frequency. So here, your break frequency, let's say omega sub b, is 1. So now let's look at what h of J1 has for a magnitude. This is now 1 over J1 plus 1. We've now replaced S with J1. And if we wanted the magnitude of that, that's now 1 over. So I've taken the magnitude of 1, that's 1, divided by the magnitude of my denominator factor. And what's the distance between? So here, thinking about this, you could say, oh, if I'm right here at minus 1, I walk over 1 and I go up J1, and that puts me to that point. And I'm really asking, what's the hypotenuse? This is now the length of 1 plus J. Which, in fact, is the real part squared plus the imaginary part squared, 1 over the square root of 2. And what is that magnitude in dB? That's now 20 log base 10 of 1 over the square root of 2. Everybody's looking for our chart for logs and dB, right? This is now 20 times log of 1 minus log square root of 2. This is 0, and this one we can clean up a little bit if we say, oh, that's now 2 to the 1/2. Or that's now 10, and I forgot my minus sign. That's minus 10 log of 2. Log of 2, 0.3, right? With your calculator. So this is now minus 3 dB. Now, suppose somebody says, well, I want more attenuation at higher frequencies. They say, I need a bigger order filter. If they now say, oh, well, I can still get or obtain the transfer function that I want if I just add more filtering, just add another filter. Does that preserve the same bandwidth? Is my magnitude at 1, both poles are at minus 1, right? Both poles are at minus 1, and I'm going to have a roll-off of minus 40 dB per decade. But have I preserved my 3 dB bandwidth at omega equal to 1? Now I have this. And I should have said that's the magnitude. I now have 1 over the square root squared of 1 squared plus 1 squared. Now I'm at 1/2, not 1 over the square root of 2. Instead of at 0.707, I'm at 0.5. So that now, by getting more filtering by just not arbitrarily, but by trying to add in cascade, in combination, the same filter stage together, just keep stacking them up, because that will give me more roll-off. And I thought it would give me the same behavior. In fact, this now compromises our magnitude. Now, our straight line plot is okay, but now instead of being at minus 3 dB, we're down at minus 6 dB, so my actual curve is more like that, and my 3 dB frequency, instead of being here at omega equal to 1, it's less. This is now my dilemma. I now said, and I hope I've convinced you, that you can't just keep combining these simple factors and preserve maybe the bandwidth that you anticipated you might be able to achieve. You can't just say, oh, I have a 1 over s plus 1 factor. That gives me just what I want. I want more attenuation. Let me just add another one. Combine them so that I have this factor 1 over s plus 1 squared. Now I hope I've convinced you that that's not going to work if you're trying to maintain a 3 dB frequency or your cutoff frequency at 1 radian per second. We're going to have to be more creative. Did anybody have breakfast this morning? No. No time for breakfast? Oh, you have to make time for breakfast, especially when we're talking about filtering. Huh? So did anybody have pancakes for breakfast? You wish. What do we think about pancakes? They're delicious. Besides being tasty, they are flat, aren't they? Flat as a pancake. Well, we want to try to maintain this flat magnitude response as long as we can, and then bend over right at the last minute and go through the same frequency of 1 for any of the order of filters we want to design. So we want our magnitude plot to be flat, maximally flat, and the way that we do that is with Butterworth filters. Do you see the pancake reference? So we have Butterworth syrup that we put on these flat as a pancake. Okay, humor me. Tomorrow, get up and have pancakes. Get some Butterworth. Go down the grocery aisle and say, well, I'm just looking for filters. Well, the coffee filters are somewhere. No, I need Butterworth filter. We still have a minute to enjoy our time together. So we are going to pick up next time in a week figuring out how do we design Butterworth filters, because we want to overcome this dilemma. We want to make sure that if we increase the filter order to 2 to 3 to 4, we still keep our cutoff frequency at 1. And that's going to mean that we can't just keep adding poles at -1. We have to create our pole pattern in a Butterworth pole pattern. And we're going to learn how to create Butterworth pole patterns in a week. And if you're anxious, you can read about that over break. We'll see you in a week. Enjoy your break.